thank you all. Thank you for coming. It's a Saturday night. And okay, my name is Rishab Navaneet, and today I'll be telling you about my current master's research project, which is harvesting energy from noise. So, as a good place to start, see, among all the sources of energy we know in nature, like solar energy, wind energy, and all, there is one source of energy which is present everywhere, but which has a lot of energy stored in it, but still we don't use it. We literally not use it at all, and that is the energy in noise. And by noise, I don't only mean the noise from traffic or sound pollutions. Noise includes all small scale movements. It's a quite a broad definition. Small scale movements like the wind blowing, like small breeze, mechanical vibrations, our body movements, ripples in water, all such small movements in which we cannot go and put a dynamo there and extract energy using a generator. So for a lot of time, this energy in all these waves and all, it was not accessible to us because of lack of infrastructure, and the economical gain we get is much less than the economic we have to put in. But that has changed now. Okay, so now we have something called nanogenerator. Those small finger like projections you see, each of them is like 20 to 30 nanometers in width. Okay, really tiny, like maybe say 52 nanometer, 52 picometer is the size of hydrogen atom. So it's like 1000 hydrogen atoms wide. And on a like 1 centimeter by 1 centimeter sample, you can grow like billions and trillions of them. And each of them, each that tiny projection you see, those are piezoelectric crystals. So each of them, when we apply a mechanical force, they can convert that energy into electrical voltage. Each of the small finger-like projections can generate 0.3 to almost 1 volts, each of those projections. But definitely the current will be limited. So like when we have a lot of them connected parallel, we will be getting a good amount of current from this. And the application of this thing is really huge. It's not only about like harvesting energy. Okay, we'll start with harvesting energy. Just think about it. Like the curtains that you hang on the wall, they are simply sitting there and fluttering in wind. If we grow this zinc oxide nanowires can be grown on any substrate. So we can grow them on that cloth also. So with that cloth, with that much surface area, when we generate energy, it will be a significant amount of energy generated from just that blowing wind curtain. Or imagine your pants or your shirt being able to like convert your movements and give you warmth and cold. Just convert that energy into heat and give you warmth and cold. Or think about, yeah, or think about just your like phone in your pocket being able to charge just from your motion. So like converting these small noises or our body movements into energy has a lot of potential. And apart from that, apart from the ability to convert energy, these piezoelectric nanocrystals, I told you, like they can convert mechanical energy to electrical energy. But the opposite is also true. They can take electrical energy and convert it to mechanical energy. So similarly, another important research that is happening in this field is, we know VR headsets, right? VR headsets, we can see, like we can visualize something that is not present just like how it is in front of us. But one thing missing in VR is sense of touch. We can never physically feel something which is there. So by using these nanogenerators, if we apply a voltage across this nanogenerator, it will stretch. 1 nanogenerator will stretch if we apply a voltage. So by carefully providing voltages to selected points in this nanogenerator crystal, you can simulate sense of touch by wearing a gloves, and on that gloves different points will be connected to different like circuits, and by simulating the perfect circuit, like you can simulate touch. And actually there are much more to say, but this is actually a very versatile instrument, and today we will be learning about its applications. Yeah, but before that, this is me generating. This is a sample of zinc oxide crystal that is grown. This is a sample containing zinc oxide nanowires grown, and we were testing the output properties, and see, that was under small tapping. Now under harder tappings, like you were getting nearly 0.1 volts of energy from, sorry, 0.1 volts of voltage from that sample. And yeah, so why did I tell you this? I told you this to just get your interest in this topic. Okay, so in today's presentation we will be seeing what piezoelectric nanogenerators are, how we make them, how to measure the output voltages, the future like researches that can be done, my research work that I have done. And Gaurav has given me 45 minutes to talk. Like maybe like if I have some time left, I'll probably go into some other research works I'm doing. Okay, so let's start. So first, to make sure that we are all on the same page, we'll start by introducing piezoelectricity. So piezoelectricity is a property that some crystals, some specific crystals show, and the property is that when we compress those crystals, they will generate a voltage across them. So they help in converting mechanical energy to electrical energy. And all crystals cannot show this property. They are shown only by crystals that don't have a central symmetry. So the basic idea behind piezoelectricity is, in every crystal there is positive ions and negative ions. So when we compress a crystal, if positive ions move to one side and negative ions move to another side, then there will be charge separation and then there will be voltage. But if a crystal is centrally symmetric, like this one, when you compress this crystal, these two will come closer and these two will move further apart. There won't be much voltage, and like the average position of charges won't change. But like in the second case, mouse pointer is not like in this case, in the non-central symmetric case, okay, I have a better place. So consider this collection of atoms which is taken from the center. Okay, right now the red represents the positive cations. So on average the positive charge is located at the center, and on average the negative charge is also located at the center. Now when we compress the crystal, the charges will move. Yeah, and as you can see, like the more negative charges come down and positive charges go up, and there will be a charge separation, and in the bulk of the crystal these charge separations get neutralized, but only on the surface you will have a one plus layer on top and one negative layer at the bottom. This is piezoelectricity. This property will be shown by almost all crystals that have hexagonal closed pack structure, because in HCP structure there is no central symmetry. Okay, now this was a 2D model. Here you could see one red atom is surrounded by 3 blue atoms. Zinc oxide is a crystal that looks like this. It is just a 3D version of what we just saw. Here one zinc 2+ atom, which is shown in gray, is surrounded by 3 yellow like oxygen atoms. Okay, and when we compress the crystal, same happens. When we compress it along the C axis, this Z axis, charge separation happens, and one side of the plate becomes positive and the other side becomes negative. Apart from the piezoelectric properties, zinc oxide also has 2 or 3 other properties. Zinc oxide is a semiconductor, and it is a it's a semiconductor in the UV region. Its band gap energy is almost in UV region, so it very easily absorbs UV radiation. So that's why, like, I think almost all the sunscreens we use, they use zinc oxide. All medicines we use have zinc oxide. These Australian cricketers, when they play test matches, they put a white thing on their face now. That is zinc oxide. It's almost used everywhere, and one problem with zinc oxide is that it has its energy gap is in the UV region. It's very easy to take electrons to conduction band. So there will always be free electrons in it, and this free electrons is our biggest enemy, like as you will see later. The presence of free electrons very much hinders piezoelectricity. Yeah, so that's about zinc oxide. Now nanowires. Nanowires, I've already told you, they are crystals with a high aspect ratio. Like breadth and length are very small, height is very large. And these crystals are actually very small. Their breadth is around 50 nanometers. And at that scale, quantum mechanical effects start to play. Okay, like in a normal crystal, an electron can take any energy level. But in these crystals, along the length and breadth direction, it is almost like a 3D potential well. Sorry, 2D potential well. Like you are not like only quantized energy levels are possible, and because of that, these also have some very interesting properties which are not related, so I won't go into that. They have almost infinite conductivity, which we will see later. Yeah, so I hope you got a basic idea of what piezoelectricity is, what nanowires are, and yeah, like the zinc oxide crystal. So now we'll enter into the topic. Yeah, so as I told you, since zinc oxide is piezoelectric, obviously zinc oxide nanowires will also be piezoelectric. But apart from the piezoelectric properties, they also show a property of flexoelectricity. This is like, normally a crystal is very strong, we cannot bend it. But since this has a very high aspect ratio, it's possible for us to bend this crystal. So when it flutters, when it bends, it generates a voltage, which is apart from the piezoelectric voltage, we also get a different voltage which is called flexoelectric voltage. And the property of zinc oxide is that the flexoelectric coefficient of zinc oxide is very high. You can generate like 0.405 volts from just flexing it. No other crystal offers that much high flexoelectric coefficient. So apart from piezoelectric effect, we also have flexoelectric effect in zinc oxide nanowires. And because of the high aspect ratio, that is like high length to breadth ratio, see there was a yeah, okay, so there was a theoretical analysis of zinc oxide crystal done. Okay, in that it was shown that the piezoelectric output voltage is inversely proportional to the breadth of the nanowire and independent of the length of the nanowire. Yeah, basically independent of length of nanowire. So this inverse proportionality to breadth is very important because we are dealing with 50 nanometers, so we will be getting very high amount of voltage. So that is one advantage of nanowires. And presence of electrons is like, yeah, so yeah, this was the, no, I had it here. This is the analysis that they have done using a hexagonal crystal, assuming that there is no free electrons. They calculated that there will be around like 0.7, like almost 6 volts of energy or 1 volt of energy, 1 volt of voltage can be generated. But in real life, our crystals have free electrons, and what happens is the presence of free electrons, when there is a charge separation created, there will be plus there and minus here. The free electrons in the crystal, they will migrate to that plus side and neutralize all the plus. So we won't get as much voltage as we expect. Yeah. So this is what they theoretically calculated. This side will be plus. Okay. Left side will be plus and right side will be minus. That is what we were expecting. But in practice, we got something like this. Here, I think I have reached my limit of zooming. This, from here to here, this here is the nanowire. So at the negative side, we are getting nearly 0.2 volts, but on the positive side, we are getting nearly 0.03 volt. That reduction in potential is because of the free electrons. Okay, so nanowires are very good in generating electricity, generating piezoelectricity. Our only problem is we just need to get rid of this free electron somehow. Okay, now we'll go see how to grow zinc oxide nanowires. So growing zinc oxide nanowires, there are basically 3 methods, and depending on what we are growing zinc oxide nanowires for, each method has its own benefits and losses. First method is very vague. Okay, first let me tell you what we require from the nanowires. Okay, we saw that piezoelectricity is possible only along that C axis. So all our nanowires should be oriented in C axis. That orientation, everything should be hexagonal and standing straight, that should be there. Now secondly, we are planning to grow it on flexible substrates like plastic, cloth and all. So it should not be a very high temperature process because our clothes should not be damaged. And thirdly, our requirement is that we should be able to control how the density of nanowires. If we have so many nanowires very close to each other, they will overlap, and even they overlap like this, the voltage is less. Obviously, when they are independently standing, then the voltage is maximum. So to make sure so these are the 3 requirements that we want. We should be able to control density, temperature should be low, and all should be C axis oriented. So in template assisted synthesis, what we do is we take a silicon dioxide alumina template with so many holes in it, and we just apply pressure and put in zinc and heat it, and zinc will turn into zinc oxide in presence of air. It's a very lame way of doing it because we don't have orientation at all in the crystal. Like a zinc oxide can go inside the hole in any orientation. So all crystals won't be oriented along the 002 axis plane. So that is bad. So we won't be using template assisted synthesis. Vapor liquid solid method is a very good method. But this is actually a very costly method. The idea is, if you heat zinc in presence of oxygen, in the presence of a catalyst gold, it will convert to zinc oxide. We want zinc oxide nanowires. So we use gold nanoparticles. We deposit gold nanoparticles, okay, on a surface. We will deposit gold nanoparticles in yellow, and what happens is, yeah, when we heat it in presence of zinc, growth will happen only at the place where catalyst is present. So the catalyst is nano, so the nanowire coming out will also be nano. But the problem is, in the end, there will be a small bulb of gold on top. So that bulb of gold on top will neutralize the positive and negatives. In previous slide, I showed you this side is positive and this side is negative. If there is a conducting gold on top here, that will just neutralize the plus and minus. So charge separations won't stay in vapor liquid solid method. So then there is a method called hydrothermal growth. It's a totally chemical growth method. in which we use some chemicals, we put it in water, like we wait for some time, growth will happen. This is nice. This requires only temperatures up to 80-85 degrees Celsius, and the zinc oxide nanowires grown will be very close to each other, but by controlling how much chemicals we put, by varying the concentration, we can control the density of nanowires grown. So comparing all the methods and comparing the X-ray diffraction data of all three methods, we see this is for the first one. There is 002 peak is what we want, other two peaks we don't want. Okay, so there is a significant amount of zinc oxide which is oriented in other directions. Here it is very less, but there are other peaks of other atoms, Al2O3 and all. The silica peaks are there. And then there is hydrothermal method where 002 is very prominent, but there are other small peaks corresponding to silver and all. But that is okay. Silver seed, zinc oxide seed, you can see like on the top. All other peaks are very small. Only 002 peak is huge. So in our lab, we will be using this this hydrothermal method to grow the nanowires. So I'll show you like my research work later. So after growing nanowires, we need to measure the piezoelectric output. To measure the piezoelectric output, what we do is we keep an electrode on top and an electrode at bottom. We tap on it and we check the output. That will give you the piezoelectric output. That is very easy to measure, and that is measured like this. The bottom here, see there is a zinc oxide layer. So these are the zinc oxide. That horizontal bars are the vertical bars. These are the zinc oxide nanowires, and on top of those nanowires we deposit a copper type electrode, and bottom is already conducting because we grew it on a conducting surface. So by measuring the voltage, we can find the piezoelectric properties. But to measure the flexoelectric properties, this cannot be done. Like for flexoelectric properties, to see like that flexoelectric voltage, if we stick a copper tape and pull it from here, the tape will just come off, like it won't bend the crystals. So to bend the crystals, you need this zigzag electrode on top. These are like created, those zigzags are like 50 nanometer thick zigzags. So to create them, like we will be using some etching process, that is a silicon electrode created using some etching process. I forgot the name actually, directional etching or something is there. So yeah, so we choose one of the electrodes, and also it matters what material we use for electrodes. Okay, see, ultimately we are harvesting energy from noise, and noise will average out to zero. Like some crystals it will be positive voltage, some crystals it will be negative voltage, and so if we want to extract energy, we need a rectifier. Somewhere like we should rectify the circuit. So since zinc oxide is a semiconductor and the electrode we are keeping is a metal, the type of junction that forms between the metal and semiconductor matters. And by choosing the proper metal semiconductor junction, we can make sure like negative voltages won't go. Like by choosing a proper Schottky junction, we can make sure the voltage is rectified there itself. So for that, we have to go search all the metals and find out metals with higher work function than this thing, zinc oxide. And we have like three. This silver, there are many actually, but in our lab we are having these three things: silver, aluminum, copper. So silver nanowires, sorry, silver electrode will form, okay, sorry, I forgot to mention, zinc oxide has a work function of 4.1. So anything greater than 4.1 will form a Schottky diode. So like this copper is having 4.53 to 5.1. So it will form a very good Schottky diode with like 0.8 to 1 volt of that barrier potential. Yeah. So yeah, we will, in my work, I first grew zinc oxide nanowires on glass. It was not a normal glass, it was a conducting glass. It's called FTO coated glass. And after growing, it looks like this. This glass is actually transparent, but after depositing zinc oxide, it will become like this. And after depositing, after growing zinc oxide nanowires, it's like a 1-day process. We take it, stick a copper tape on top, and take 2 electrode lines, and it will look like this. And after taking the electrodes, I am supposed to like tap the crystal and check the voltage output. So for tapping, like if I tap with my hand, it will be non-uniform. Like for research purpose, when I'm doing, I should be like doing it with a something. Yeah. So this is a simple Arduino based tapping mechanism. I can control the that frequency of tapping. It can go up to like 100 hertz, all the way from like 1 hertz. So we designed a tapping mechanism, and after that we checked the VI characteristics. So see, the VI characteristics does resemble that of a diode. So this shows that like it was a success, like a Schottky diode has been formed between copper and zinc oxide. And we were seeing like a knee voltage. This is the actual plot. This is a log plot, and we were seeing like at 0.8 volts there was a barrier potential. Like at 0.8 was the knee voltage. So the growth was successful. After that, we tried measuring the piezoelectric output. Oh yeah, I forgot to show you one thing. There was something interesting. Like first we performed the like in the dark versus in the light, the IV characteristics were different. So that shows some, yeah, like in the presence of light, some photoelectric effect was happening. Not photoelectric, like photovoltaic effects were happening. Yeah. So in the piezoelectric output, yeah, this was what this is the voltage we got when we tapped versus current versus the power output. We were getting nearly 0.003 volts, which is very less compared to the theoretical predictions and very less compared to other papers also. Like they were getting around 0.03. I'm 10 times less, so we have to work more on that. And we were getting a power output of around 10 nano watts. This was from a 1 centimeter by 1 centimeter sample. By taking a bigger sample, we will be getting more voltages. And one more thing, this was totally based on piezoelectric effect. Like we couldn't use that flexoelectric effect because we didn't have that zigzag electrode. So by incorporating both of that, we should be getting a higher voltage. But right now we got a peak to peak voltage of 0.004 volt and 2 microamps of current and a peak to peak 10 nanowatts of power. Okay, and the IV characteristics on the left, it resembles that of a solar cell, which is as expected. Now, yeah, now we also check the under tapping, like how much time it takes after generating a voltage to recover from that voltage, how much time it was taking. So as you can see, like this was the Arduino's microcontroller data, like serial monitor data. We analyzed one peak. This one peak is here. So we analyzed how much time it is taking for it to saturate. We got a 7.5 milliseconds of this thing, characteristic time for saturation, relaxation time, by taking it average for all. There should be, yeah. That is why we designed this thing actually for. We designed the tapping mechanism to see the frequency response. At which frequency, like we are getting maximum average power output. Yeah, that's true. Like there should be a resonating frequency where we'll be getting higher maximum. Good. Okay, so like as we saw, there was a difference in dark versus light IV characteristic now. So we just did a test, like we were exposing our crystal to sunlight for in 20-second intervals, and each time we exposed it to sunlight, we got like 0.6 microamps of current, and that was a sudden burst of current. Then it decayed, and it was decaying and saturating to almost 0.15 microamps of current. Yeah, so we were getting like a short circuit current of 0.6 microamps from the zinc oxide nanowires. Yeah, and that's it. So this was all I have done till now. So our future plan is like to either improve, see that n-type semiconductor, the extra presence of electrons is the biggest issue that is reducing the voltage. So our plan is like we will dope zinc oxide with lithium atoms. So lithium is p-type, so like lithium will like reduce the number of free electrons in the crystal, and that will probably increase conductivity, sorry, increase the piezoelectric output. Also, we just tested it on FTO coated glass. We now need to change to flexible substrates. Flexible substrates, yeah, we will deposit on flexible substrates, and in flexible substrates, we may not need a zigzag electrode to create flexoelectric effect. We can flex the substrate itself to create flexoelectric effect. And zigzag top electrodes, and yeah, sensor designs. See, this zinc oxide nanowires, they also have a very interesting property, like they just like by mechanical compressions can be converted into electrical pulses. That means they can be used to measure heart rate, they can be used to measure any body movements, and this zinc oxide nanowires, their output voltage depends on presence of impurities. If there is like some nitrogen gas present, the output will be different. So they can be used to sense gas. Yeah, gas sensors can be made. So there are many sensors that can be made out of this, and these sensors, they can be like maybe self-powering. Like if it is, say for example, heart rate monitor, like it's quite ambitious goal, but like we could extract energy from our pulses itself to like detect the pulse rate. It's not maybe possible, not sure, but sensor design is a very hopeful field that follows. Probably can be, yeah. We may be needing a battery source, like when heart beats. Oh yeah. Okay, so to conclude, today we saw the potential of zinc oxide nanogenerators. We learned the piezoelectric properties and how to make zinc oxide nanowires and all of that. We saw, like I showed you my work and prospects of improvements. Now, yeah. Okay, I have, yeah, so I have come to my end of presentation. Thank you all, thank you for listening. Now, these are my other works. I don't think I have time to discuss. Hopefully, like some other day, maybe. Yeah, maybe some other day we'll discuss all this.